In this lecture, we're going to cover the particulars of gravimetric analysis, including steps to take to get the best results. The ideal precipitate is fairly insoluble, easy to filter, and has a known constant composition even when subjected to heating to remove excess solvent. While few substances meet all of these requirements, the techniques described in this section will help optimize each property of an ideal precipitate. Crystal growth occurs in two phases. During nucleation, dissolved particles form small crystalline aggregates on insoluble particles or scratches in the glassware. Solute particles then add to the existing aggregate to form the larger crystal. To optimize the growth of large crystals that are easy to filter, we want to avoid making a supersaturated solution. We can do this by raising the temperature, adding the precipitant slowly, and keeping the solution concentrations low. If we don't, nucleation will proceed faster than particle growth, causing many tiny crystals to form that may pass through or even clog our filter. Usually, precipitation is initiated by mixing a solution of precipitant directly with a solution of analyte. Here, we see a different method. This method of homogeneous precipitation allows the generation of precipitant in the solution through a chemical reaction that keeps the concentration of precipitant low. In this example, the decomposition of urea by boiling it in water produces hydroxide ion. This hydroxide ion goes on to neutralize formic acid, forming formate ion. 3 moles of formate ion then react with our iron 3, which is our analyte of interest. So this is what we're trying to precipitate out. We see that we made this iron 3 formate complex with several waters of hydration associated with it. We see this downward arrow, which is emphasizing that this precipitates out as a solid. Several homogeneous precipitation reagents and the ions they precipitate are listed here for your reference. Don't feel obligated to memorize this list. It's here as an example of the wider variety of cool chemistry you now have at your disposal as an analytical chemist. We've already seen how urea can be boiled to produce hydroxide ion in solution to precipitate some of these elements. Another neat reaction is to use dimethyl oxalate to produce oxalate C2O4 2-, which is an excellent chelating agent for divalent metal ions. Ionic compounds are usually precipitated in the presence of added electrolytes. If we consider the case of silver chloride, we see a colloidal particle of silver chloride growing in solution. This particle will have a net positive charge due to the silver ions adsorbed or attached to the surface. This is not to be confused with absorbed ions, which penetrate beyond the surface of the colloid or solid. The net positive charge on the colloid surface attracts the nitrate anions and repels the cations, creating an ionic atmosphere. This presents a problem because colloids must collide with one another to form solids that are large enough to be filtered. Increasing the concentration of nitric acid in the precipitation reaction decreases the thickness of this ionic atmosphere. This allows particles to come closer before repulsions become significant. For this reason, most gravimetric precipitations are done in the presence of electrolyte, and the solid will be rinsed with this same electrolyte solution to prevent that charge from building up and breaking apart the solid in a process known as peptization. Digestion is the process of allowing the solid precipitate to stand in contact with the mother liquor, usually with heating, so that the solid slowly recrystallizes into larger particles while also expelling impurities during the recrystallization process. A co-precipitate occurs when a substance whose solubility is not exceeded precipitates with a substance whose solubility has been exceeded. These co-precipitated impurities can be adsorbed or stuck to the surface, included, or occupying a lattice site within a crystal or occluded, meaning the impurity is trapped, sometimes with solvent, inside a growing crystal. To remove these trace impurities, we can wash away the solution, dissolve the solid, then re-precipitate, often reducing the amount of co-precipitants. However, we can use co-precipitation to our advantage to concentrate a trace analyte in a process known as gathering. The precipitate is collected, dissolved in a small volume of solvent, and the concentration is increased enough to be analyzed accurately. Some impurities can be treated with a masking agent. For example, if we wanted to determine the concentration of beryllium, magnesium, calcium, or barium with N-para-chlorophenylcinnamohydroxamic acid, which is usually just called RH for obvious reasons, we see that similar ions such as silver, manganese, zinc, cadmium will also react with RH. If we treat the solution with a significant amount of cyanide, Cn-, before adding the precipitating agent, cyanide will form soluble complexes with these interfering ions that keeps them in solution and keeps them from reacting with our precipitating agent.